Good. So let's trying to recall what we did last time. This and put this where else? So last time we considered stochastic differential equation dc d psi of t a psi of t dt plus sigma psi of t twt multidimensional with multiple Brownian motion, generally speaking, so it's better to write something like this here in Rm, and psi then lives in Rd. So sigma is m times d matrix. And we discussed that if coefficients are defined, sigma are given only in a domain that is a connected open set, we still can define a solution psi as a process effectively, well, stopped upon hitting boundary. And we said that if you want to have more advanced behavior near the boundary, we need to do through a lot of work to add another layer. But generally speaking, it's defined up to the moment of leaving exhaustion. So we considered set of compact sets. That's such that their union is our D, and if tau n is the first moment our process psi leaves dn, or hits the boundary of dn, more properly to say that one can try to consider the limit of this, and up to this moment of time everything is well defined. What happens at this moment of time is a bit trickier in the sense that if process really hits the boundary, we stop it here, but one can produce examples of processes that actually never hit boundary. But so for instance, just consider something living in a, like say, a block and moving here as a Wiener process and here moving in such a way that it never hits the boundary. Because Wiener process like essentially covers the whole line by the law of iterate logarithm, so might be easier even to consider just upper half plane. Here it behaves like a Wiener process, and here it behaves as some process that never hits this point zero. Assumes that coordinates are independent. That means that effectively that this tau doesn't exist, but there is no, like, even the limit of our process when this happens. It just oscillates, gets as close to the real line as you want, but it never hits it. So there might be some problematic behaviors near this boundary, but it just means that this tau is an infinity in our case. So everything is still well defined because take any epsilon, and up to that moment the process is well defined. Take any epsilon up to the moment hitting of this level, new level epsilon, it's still well defined. So it's something that really exists. So, and we stopped before discussing a bit artificial case. So what happens if case 2, coefficients A and sigma are given on closed, on a closed. This is more of artificial situation because this covers everything you need. If it's defined on a closed boundary, it's still defined on a closed set, it's still defined on the interior of the set, and this construction works. So this construction allows more general situations, and overall is just essentially what you ever need. However, there are like some illuminating remarks that can be made here, and also I think that it is a general useful information for most of our participants. So for simplicity, I assume that autonomous, that is time dependent, independent. No. There are like a different situation here. So if a sigma Lipschitz continuous, one can extend them explicitly to the whole space. And essentially, Lipschitz continuous, and the same is true for Holder continuous function, as far as I recall, can be extended from any set. It doesn't need to be closed, it doesn't need to be open, and one standard is some extension that you just take. If you want to extend the Lipschitz continuous function, you just take infinitum all points from the original set, takes Lipschitz constants for f, the distance to that set plus the original. This is going to be the Lipschitz extension. If A and sigma are merely continuous, its corresponding extension still exists. It's quite easy to get it bounded if A sigma were bounded, which is effectively means it's only A. The set was bounded, effectively. It's a separate statement. This is related to so-called Orson's lemma. Now, if A and sigma are Ck on D, and here we need to understand what this means. This means that it has K continuous derivatives, including mixed derivatives up to the order K, the total order K, but on a closed set. So there are two ways to understand this. Typically, in most books, it means that A and sigma are still defined on some neighborhood, and that means that for any point of D, there is a neighborhood which is differentiable in a proper sense. But here, we understand it as slightly different notions. One can Google something, because actually it's somewhat hard to find a proper reference, not going for differential geometry. Courses on calculus typically do not read this equation at all. The Whitney extension here works. And it's based on such notions as partitions of unity. I'm not going to discuss this because it takes a lot of time to actually prove this. But overall, partitions of unity are very useful tool. So I recommend reading books on some textbooks about PDEs to learn about the existence of such stuff. Essentially, this is an infinite cover of the whole line by some functions as complex supports it sum to one, and locally it's a finite cover, and they are compatible with this D in some sense. So there exists this Whitney extension theorem that allows you to do such extensions, or maybe you can do this just directly by applying partitions of unity if you have slightly better situations. And here you mean that it has derivatives in the sense of Taylor expansions. They are compatible in the sense Taylor expansions, and so the first derivative is going to be admit something like, in one-dimensional case, I'm writing it for simplicity. This is first derivative, and this O is locally uniformly on D. And the same holds for all the derivatives up to time k. So if they're compatible with the set, which is always true for the Taylor expansion, if you have real derivatives, locally uniformly on D. then they can be extended with preservation of this property to the whole line, to the whole space. And it covers also other situations. And obviously this is going to hold if we have A and sigma satisfying CKD in the classical meaning. Given this almost no assumptions. Now, it is an interesting remark here that if A sigma are not autonomous, so they depend on T. Like this is going probably to hold. It depends on how T is incorporated in A and sigma. Typically, since A and sigma incorporated in a locally uniform way, which stems to Lipschitz continuity, it should work. But now, I am not aware of any extensions of the Whitney extension theorem that cover the case when, say, A and sigma are only of this type or something like that. So they are parabolic in some sense. This is an interesting example that this situation where something has more derivatives with respect to time, to space than with respect to time. Sometimes it's not covered by standard differential geometry, for instance. Probably, my assumption would be that if DS has some good boundary, something can be done, or you can try to do some repeating the proof of the extension theorem by using T as a parameter. And I actually even consulted some people and they confirmed this might be the way, and under some additional assumptions on T, this might work or might not. But this is an interesting moment that it's not as easily available and one can think. But overall, if they are good, you can extend them in some way, at least if they are autonomous. But again, this situation is the most natural, it covers the most things we ever need. Now, at last, we can formulate some rigorous results. Because this also was rigorous. This stuff was rigorous, but it was more like for general education. Because again, such type as the Whitney extension theorem, partitions as unity, for some reason, are almost never covered in calculus, in courses of calculus. And I honestly think this is not really a correct way to do things. But so let D be a domain connected open set in Rd, and I will need to introduce notation that psi xt is a solution of d psi xt of S equals a psi t s s ds plus sigma psi xt of S s d w s. So we fixed x, we fix t, and psi x t is equal to x, and here s is greater than t. So x, t is a starting point. Now we can consider solutions that start from x at time t, and s is greater than t. Now, formally, we never considered SDEs that live on unbounded interval, but it's pretty clear, should be clear that you can do this. You just consider SDEs on intervals of this form for any n, and in a very similar manner to how it happens here, you can then define the solution of the SD and the whole real line. The only problem that is not, you can't really write something like this for obvious reasons, but for every fixed t is going to be convergent integral. And obviously, for different and capital, they're going to be compatible. So again, let us recall, I will actually switch to B here because it's how it's often done. I will need, so B here is a B1, BD. Sigma is a matrix. Sigma. E ranges from 1 to D, J ranges from N to M, and there is no really relation between D and M right now. And set.
Sorry, and here we have 0, right? So this is the initial condition, or
No. T, 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 T.
T. Okay, so it's like a stochastic flow, something like this.
No. Well,
Mm,
stochastic flow would require some connection between for different axes.
yes.
We
Uh,
don't really consider anything that relates these solutions for different axes in this part of the course. We will, on the next lecture, actually speak about flows a bit.
I
But
mean, just in terms of the notation, yes. So we have 2 points
yes, we
instead
have
of
to start.
starting from 0.
We are starting from T.
Yeah. Okay. So I get the notation. Thank you.
We are starting from T. So like psi x0 is what we used to work before. Indeed.
Mhm.
But now we allow ourselves to start at T, and obviously it doesn't really change if we consider process on such domain or something like that. It doesn't really change anything. It just shifts everything. And that's all. But yes, it's very related to the notion of the flow. And now we're going to establish some stochastic representation of solution of some PDEs, and to do it in a reverse way, that is to consider uh, some function and prove that it solves PDE if this function given in a proper probabilistic form. One can use flows. There are like other methods, I think. But flows is a very important tool. So actually, we will still need flows and some properties of such families. But next lecture, I need to define such object. So AEG is just sum over K from 1 to M, sigma IK, sigma JK. So this matrix forgets about W's. It even forgets about the number of W. Under some assumptions, so for instance, A is uniformly elliptic, this, uh, if you speak about matrices without any assumptions, without any dependencies of some parameters as x and t, if this is positive definite, this sigma is actually unique in a proper sense. But we don't really need it. I want the following differential operator of the second order. And now we are ready to at last get to some interesting results. This is the Feynman-Kac. So the formulation is like this. Let O U from 0 to T capital to R be such that. Now, firstly, we required to have two continuous derivatives with respect to all special variables. One derivative with respect to time. So this is this notation. D0T, obviously in the interior, because it's not clear what the derivative on the boundary is. And it's continuous on the closure of this domain. And there exists some C such that UXT is uniformly with respect to T satisfies this. It satisfies the following equation again inside of the domain. And it satisfies boundary and initial value condition. So this is initial value, initial condition, x belonging to the closure, and it equals some function gxt if t belongs from 0 to capital. I'm just writing t from 0 to t capital because it's already given at t capital. Now we need some assumptions on these functions. So typical assumptions that I needed here are just they're bounded. And say continuous. But it's not needed for all of them, to be honest. And we also require compatibility condition. We will get rid of it eventually. So jxt equals phi of x on the boundary. So I can put here a square bracket and nothing changes. It's just compatible. Set or define tau xt is infinium. It's either t capital or infinium of those s belonging from 0 to t capital, excluding the psi xt of s t belongs to the boundary. It may never happen, but it's still a finite expression. Then uxt admits the following probabilistic representation. So it's mathematical representation jxt tau xt tau xt, this part, et tau xt. I will write what this is in a moment. Indicator that tau xt less than t capital. If it's his boundary, it is given by this behavior on the boundary. If it lives inside of the domain up to time t capital is given by its terminal condition. I said it's initial value, but it's written on the right hand side of the interval. But you can rewrite everything in terms of a more standard formulation when you have your really initial value condition. But here it gets more unpleasant to write this expression because you need to do some change of variable. We will see actually how it's done. Minus
So it's like the final value.
No, terminal. I think the proper term is terminal.
Okay.
It's quite interesting why it holds here because like this is how nature is actually it of s ds. Let me look at it. Now look at this minus. It should be here. So everything is, and here it of s is and I think I need to put minus or not. Let's think. No, I don't. I think I don't. Integral from t to s. This is exponential. Sig psi xt of r dr dr. So this is a very important result, a very well-known result. It was established in a slightly different form. It was established on an attempt to give some understanding, to provide some understanding and give some meaning to so-called Feynman-Kac integrals. There are like at least two ways to define them rigorously in the physical world. And overall, this links PDEs and as it is. This
Oh,
is the first
sorry.
step.
And what is the function C?
Here.
Okay, so from this uh, partial differential equation.
Yeah. It's a clean rate. Now, if you think about what happens here, this is like, to be more precise in the physical sense, you need to write it in the divergence form. But effectively, this A consists of two terms. This describes, again, to be more precise and to really give everything physical value, you need to be written in the divergence form, but we still can do this here. So this describes the behavior of the random medium our particles evolve in. So psi xt is a particle, it lives, and we average over all such ensembles of particles that start at all possible positions, which are given by xt, and we average of all possible behaviors of such particles. So this describes random medium we are in. This describes physical force that pushes our particle, like external, not even flux, but like something that pushes a wave, etc. Here describes what is called killing, or if C is positive, what describes birth of our process. It can be written more informally, but it takes some time. So that's why C, we require C to be bounded, but effectively it just needs to be bounded from above, because we cannot allow infinite burst process to be incorporated here. We will lose integrability in general. So C should be bounded, so this is controllable, because it's exponential, it gets very quickly out of control. Typically, it's written with another sign, so typically they say that C should bound it from below, but here C should be just bounded from above, effectively. Now, this F, again, is a divergence form. It will incorporate something from B, and that is the proper way to write that. Describes sinks and sources. So this is why it's written in this form. Over the whole time our process lives, it either gets killed by this F, or so gets forced to something, or it gets some another life from some source. So this is this way. And as I said, this is the terminal condition. So if it lives up to the moment t capital, we know how it should behave. So it should be compatible with this condition. And if it hits boundary, it is stopped. And that is its value at this time should be defined in terms of this G. And again, this is a correction that describes how it was killed before. So it's very essentially physical stuff. And such expressions typically are often called like convection, advection equations, or some other ways, because how mechanical it effectively is. So recall that if you have the heat equation, it's often beneficial to think about it as some particles of heat moving. And here, if it hits the boundary, we keep like temperature in controllable way there. So this explains this part. And we know where we end. But again, you can rewrite this in the standard way with the initial value condition, but this will get this a bit more complicated to write.
I see,
Again,
thank you.
sorry?
I see, thank you.
You're welcome. You're welcome. Now, the conditions as they are bounded is a bit too restrictive, effectively, and continuous. For instance, it is not supposed to be continuous. There is no way it really needs to be continuous anywhere in the proof, as we will see in the line. And typically, though this is a standard formulation, you can allow these coefficients to be to have in quadratic rows. Essentially, as we will see with the proof, if all integrals that appear in the proof are controllable, maybe by the localization procedure, or etc., and can be proven to be finite, So you can get rid in a way we will see from stochastic integrals. Then it's going to work. So typically, and U and F, G, F can satisfy much more relaxed conditions in terms of growth. And C is just needs to be bounded. We can kill process as much as we want, but bound it from above, but we cannot allow it to add too much particles, to add too much heat into the picture. It will eventually lose us integrability. So let's prove it rigorously. So step one, again, let Dn be this exhaustion sequence of compact sets. That is a sequence of compact sets such that Dn interior and D is given as a union. Now, in the proof of the Ito lemma, and from the previous lecture where we did this construction, we know that one can define. This is because of this condition, though they are separated. One can define a sequence of functions, then such that every U is defined on the whole space. It has bounded derivatives of the second order with respect to time and first derivatives with respect to bounded second derivative with respect to space variables and bounded first derivative with respect to time. This B always means boundedness of all derivatives. And un just equals u on dn. You need to do some modification. We discussed it last lecture, so I'm not going to repeat this construction. Now, I will consider only the case d equal 1 and m equal to 1. Just to make it more easier to read. Now, let us apply the Ito formula to un times I on t small, t capital. So this is actually the main step of the proof. Then you have un psi xt of s, it of s minus un x t capital times 1, because it of t is just 1. And I will write this in this form. Xt, yt, s greater than t, where x of s is un psi x s s, and y of s is equal it of s. Here s from t to t capital. Now let us recall how the formula for product works. This is a good place to recall it for products. So if we have like d kappa of t equal a kappa dt plus sigma kappa dw, it depends on t. Here it depends on t. And we have e zeta of t equal a zeta of t dt plus sigma zeta of t dwt. Then the stochastic differential of a product of these two Ito processes is kappa of t d zeta of t, so zeta of t d kappa of t, plus correction. Correction has the form sigma kappa of t, sigma zeta of t, dt. Now, in our case, this doesn't have a stochastic part. So if you take kappa to be x and zeta to be y, this part doesn't appear.
And this is the joint variation, right?
Yeah,
In
this
the
is joint variation of these two martingales. Yeah. And this essentially this is a process of bounded variation, so it doesn't appear. There is no need to have a correction. So using it, we get dx of s, y of s, is what? Is it. I will skip s to simplify calculation, un plus un, everything in terms of our s. So let's do calculations. It dx un sigma dw, this is just the ordinary eta formula, a ds, first derivatives plus correction, sorry, we also almost forget the derivatives with respect to time, plus correction, which is second derivative with respect to x from un, sigma squared ds. So this is the first part, plus un, and dit of s is just c of s because we're taking derivative of exponential. So we just times c times e ds ds. Here the c is c of psi x of t s s. Now step 3. Now let us define tau n. It's an infinitum those times that psi of s hits the boundary of our dn minimum t. So it's always finite, it's well defined. And for s less than tau n, un effectively coincides with u. Because they coincide here, so all expression, if you substitute something in terms of psi x of t, works here. Note that even to apply this, we need to do some extension of psi x of t effectively to the whole to a whole space already, but we'll discuss that it's possible to do because we never discussed any version of Ito formula for processes is defined up to some stopping time. We always said that process should be defined on the whole time interval. But again, as we said last time, this is doable, so this formula can be applied. Now we get the following. Let's be careful. Un I s minus tau n is it. Now let's just rewrite this. The u sigma. This is the only stochastic part that appear in our calculations. Plus everything. This is should be un plus correction the sigma squared un plus derivative with respect to s un plus cun. And because I can get rid of those all n's by using this observation, we arrive at something like this in the terms of the original u. Now ds plus a plus c applied to u is just equal f. This is A, this is ds, this is f. So we get ds minus tau n equals it u times ut w up to this moment of time plus it f ts. So this explains our f appears again, which means that uxt, which is appears here, is going to be equal. Now taking expectations, at time tau capital, this disappears. This I put here minus mathematical expectation integral from t to t minus tau n it f psi xt of s ds. Why? Because I just wrote everything in a integral form and passed and put uxt that appears with minus in this part here and put this here. And this disappears because everything is bounded. Now we need to push to the limit with respect to n. So let's do this as a step 4. Now this part, again, everything is bounded, but if it's not bounded, you can do some type of localization procedure. We discussed a number of them already. It's going just to converge so this is a part that's already in the solution. Now let's look at this part. Ui. Let's write this psi xt tau n t capital n I t capital minimum tau. So where this like goes with n goes to plus infinity, we need to consider, to understand, we need to write it down as 2 cases. So the first case is essentially this, and when tau happens before, we need to put here you need to have one strict and one not strict inequality to not calculate something twice in this expression for obvious reasons. Now, if this is true, then we can use the terminal condition here. So it's just phi. And if it hits boundary before, this is going to be equal to g. So this is just phi psi of t. And this is g psi of tau. And note that you can play with the signs because g and phi are compatible. So it doesn't really matter where you put it. It's going to be, and that gives us this equation.
And the last equality holds in the limit, right? So before the limit we have n.
Yeah, this is close here.
Mhm.
Yeah, you're right. So if it hits before this, because everything is continuous, going to converge to this expression. If it doesn't hit or hits at the terminal point of time, this is going to converge because everything is continuous to this expression. U is continuous, so it's going to converge to the value of u at time t capital, but soon we know this that it doesn't depend on t capital, it's just given by this function, etc. So you firstly use effectively the Lebesgue dominated convergence theorem. Almost surely this is going to converge to this expression, and then you put expectation because everything is bounded. So this is exactly where you need boundness. And if you have something more relaxed than boundness, if you still can apply some version of the dominated convergence theorem, the whole situation is going to work. This is the most general form of the Feynman-Kac formula. I want to do remark. So assume that A, sigma C, G are autonomous. As I said, you can play with like G not being autonomous, etc., but this is just one example. Then we can rewrite this by using the change variables of the following form. New t is just t minus t. So and we get the Feynman-Kac formula as follows. I am not writing assumptions on coefficients, etc. The solution of dtu equals au plus cu plus if you minus f minus f minus f xt is just fx capital at the boundary is given by g. Admits the representation uxt equal again g x0 tau indicators tau x0 is less than t plus x0 tau e0 t indicators that greater than t capital and still minus psi x0 r y0 r dr. Obviously, there is no need to really write psi x of 0. You just can get rid of this 0. This is the formula of zeta. The way Feynman-Kac is often written in textbooks. Like indeed, then dtux t is affects minus dx. So this explains how you get rid of a minus and, for instance, expectation. This way, tr rdr is going to be equal in distribution to the 0. There is no r here. because this wouldn't be true. So, and since it's exactly now T prime, everything works. I will leave details to you. So this is might be more familiar version of Feynman-Kac. So what we are going to do next? So what is the plan? Oh, sorry. So plan for so firstly a bit more about the Feynman-Kac formula and the so-called method of differential equations in the theory of SDE. Now we need to at least discuss solvability of PDEs of this form and probabilistic studies. We also will squeeze something about applications to numerical schemes here and elliptic equations. Because this is Feynman-Kac formula is one direction. If we have a good solution, then it has a probabilistic representation. And it's typical how it works with application. Even if you study something from a probabilistic point of view, for instance, you consider again some exhaustion procedure, you apply some existence or and uniqueness theorems for PDEs, use the Ito formula, and this passes to the limit to explain what happens on the boundary, or whether you have this limit, etc., etc. Because typically you don't get this nice. You will need to prove that UN are convergent in this case to some. And essentially going from PDE to a probabilistic representation is much easier than trying to prove that this function solves this PDE. There are very few references you can find in this direction. And even those typically deal only with PDEs on the whole space, but not in domains. Domains put a lot of pressure on how it can be done. And honestly, I can't even give you references for cases when one starts with probabilistic representation, goes full way to prove something like this in domains. Probably if you exclude something from Malevin calculus. In Malevin calculus, this is kind of possible. Or it can be possible by using the semigroup theory, but purely probabilistic methods typically struggle with this direction. There is still some advance in this direction by Krylov, etc., but this is how it typically goes. You start with Feynman-Kac formula, or you end here. Even if you are interested in something very probabilistic. Now let's do some other versions of this, like elliptic versions. And I have somewhere an interesting example. No, it's not. Okay. Elliptic versions. So let's assume that A sigma are autonomous, and then I will write family of solutions to the corresponding SDE stopped upon hitting boundary and started at t equals 0. Let lambda be 0, greater than 0, and we are given two functions. The first function is just bounded on the closure of our domain, and U with index alpha is twice continuously differentiable inside of the domain and bounded on the closure of the domain are such that our A U lambda is equal lambda U lambda minus F in D, and U lambda on the boundary is just 0. So suppose that we know that there is a good solution of this elliptic equation. Then U lambda of x is mathematical expectation so this is still alive. To use this, we require that the process is still alive. It hasn't been stopped. And tau x is obviously just infino those s, the psi of s belongs to the boundary, if it's finite, or just infinity otherwise, if it is finite. Or infinity otherwise. Note that here we got rid of the parabolic part. We don't require this to be finite anymore. And it's still going to be well defined because we have this expectation. So let's do this proof and see how it works. Because in general, when you formulate something about elliptic versions of this parabolic Feynman-Kac formula, you have easier way to use probabilistic tools, and maybe we can have time to look a bit into that on the one hand. But on the other hand, on the other side, you need to care more about how this time behaves, because in the parabolic version, you just consider two cases: when it hits up to time t and when it doesn't. But in the elliptic case, you need to consider just finiteness of tau x, or more precisely is the existence of expectations, such expression. So again, let's consider tau x. Again, using this exhaustion procedure if needed, we can establish, I am not going to repeat all these proofs, but we are going to use the Ito formula to this expression, and we end, again, this is for t equals 0, is just 1, and for t that is smaller than tau x, we arrive at something like this. O lambda dx psi x of s sigma psi x of s dws plus, and we must get what we want. I will leave you this as an exercise. S lambda ds. So, exercise. Use Ito form. Now we want to take expectations. And this is where we need to be careful. So let's start, do it by fix some t capital and define finite versions of our stopping times. Those S. There. Compact sets that we used here. I'm putting them on step 2 because theoretically you can do this without using this exhaustion procedure here. But here we need it. Now everything is bounded, including u and phi, by assumption. And this derivative is well defined for this times. because we don't hit the boundary, so this exists. We never discuss this behavior on a boundary. We can write now O lambda psi x tau x and t So I'm just putting this random time into the Ito formula and taking expectation. This gets rid of this part because, again, this is a well-defined part. And I'm pushing this to the right-hand side. And here we get A minus lambda or lambda is just A minus just minus F. So we get minus mathematical expectation from 0 to tau x and t capital s psi x of s ds. Now I want to pass to the limit with respect to n. To pass to the limit when n goes to infinity, note that. So we have two different but everything is bounded, right? So maybe we can do it easy. Just everything is bound. What is wrong with me today? Why it works like this? Control D. So we don't. Since everything is bounded. So everything is bounded. Bounded, so we can just push to the limit with respect to n. The limit with respect to t capital is going to be trickier. Yeah. And this will us give psi x, tau x minimum t capital, lambda tau x minimum t capital. This doesn't even change. Tau x minimum t capital s f psi x s ds. Now, to get t capital go to plus infinity, we need to do some thinking. So let us consider two cases. Tau x is finite. Then obviously O lambda psi x tau x, for instance, is going to converge to what? It's going to converge to lambda psi x tau x, lambda tau x, but this is zero. It has zero boundary condition. And this is going to converge to what we need. And because we have here minus, it's going to be even bounded. Now, if tau x is equals to infinity, so it never hits boundary. So what happens with this expression? O lambda psi x tau x minimum t t is going to be bounded by the size of this function. It is bounded by our assumption. And for any t. So it just goes to 0. So in any case, this expression disappears. And thus, passing to the limit, we obtain just the representation we wanted. And now this is well defined because this is bounded and this gives integrability. So this is why we didn't really care here in this version about something about the behavior of this tau match. So this is another application of this method of differential equation that using some solutions gives some information, in this case about like Laplace transform of something, of this tau x. But one can do another example. I will not even formulate this as a theorem, I think. So again, assume that we have just this in D, and this. Assume this lambda is good enough, and phi is good enough. And again, one can prove, it's not hard, after what we already done, then this going to give you effectively information about the distribution of psi at time tau x. It gives you information about like joint distribution of tau x and the point where it hits the boundary. Now it can be done in a very similar manner that we already did. Now, if we formally put sigma just equals to 1, we get the U lambda of x. It's just the Laplace transform of this. It's not the Laplace transform, it's this expression. So if we take derivative formally, right now formally, this is going to be lambda equals 0. It's going to give us minus expectation tau x. This is formally. But that means that this function should solve because lambda v, and then we can do the inverse trick. We can start with this expression and prove that it solves, that it has this representation. So this is another standard example how you can say something about the mathematical expectation of the tau x by using elliptic equation. I will leave details to you in case you are really interesting. Now I want to formulate a theorem that imposes some conditions on behavior on tau x, and later we will see that this is not really a restrictive condition. So again, to consider elliptic case, we need autonomous coefficients for obvious reasons. Autonomous. Let's consider C is bounded here, F is bounded and continuous on the closure, and C is the same, and U is again differentiable inside and bounded on the closure, and IU minus CU plus F in D minus CU minus F should be phi. Again, tau x is the infimum boundary. It can be theoretically possibly infinity, plus infinity. We don't like immediately exclude the situation, but we impose additional conditions that says that infinity. This never happens. So if this is finite, Now, know that we need to impose some condition to make sure this is well defined. Unless we want to do some, alternatively, one can do something with this C to guarantee that this exists. But one can say about something like a bounded domain and a Wiener process. Wiener process will always leave the bounded domain, but and effectively this is going to happen. Now let's quickly discuss the proof. So again, dn as usual, exhaustion by compact sets. Again, using some possibly extensions of process, of coefficients, etc., and setting something like this would work. SFS belong to the boundary of dn, which is now always finite because of this assumption. And introducing again this correction, exponential correction, we get eventually I. So again, you will just use a proper version of the eta formula. Since everything is bounded, and this is bounded as well, we can use the Lebesgue dominated conversions to pass to the limit here, firstly with n, and secondly, essentially with t cap, like, with t small, takes the limit first to get r, and now takes the limit and goes to infinity. And this finishes the proof. Again, everything is bounded, and everything is well defined because of this assumption. This integral is well defined in particular. Again, as I said, this is not a very restrictive condition, but this is illustration. That is the previous result. We didn't really care about the behavior of tau x because we could control everything in a more natural manner. But here, because we didn't want to impose more conditions on C, well, and other parts of this expression, we need to do something with tau x. So this is the difference between parabolic case and elliptic case. In parabolic case, you don't really need to care about the behavior of tau x and something like finiteness of its expectation, but you do need to do something in elliptic case. Now, let us formulate at least one existence result. This is going to be without proofs. That is something that tells us when all the theory works. So what are really assumptions of coefficients? It's all these parabolic PDEs. I will skip the elliptic case. All these parabolic PDEs have proper, well-behaved solutions. So let us rewrite what we consider. So we consider a plus cu minus f in d times 0 t capital. We have boundary condition g, and we have condition at the right side of the interval. And I will just formulate a classical result. So we need to assume quite a lot. Bounded. And for any x belonging to the boundary, there exists some r and function such that there exists I that for any y belonging to the intersection of this portion of the boundary and this neighborhood of x, we can simplify the expression of our boundary. And this function that gives us, so this is like our boundary. This is x. And locally, it can like be given in local coordinates. And this phi for maybe like this is our d, and this is our bxr. And we have good way to describe this boundary terms like almost a flat expression. This function is bxr, and its derivatives are Holder continuous. So a typical example where this is not true is a corner, which is a very natural example. Because in corner you have something like this CD, and this is not going to be even C1. Now, there are extensions of this theorem when the boundary can be composed of a finite number of pieces that satisfy this condition. So boundary then is covered. That corner is covered, for instance. A square is uncovered because obviously this is going to be true on every this part. Especially then when you allow some type of local rotation. So instead of considering this part in this coordinate system, you can rotate and consider this coordinate system, and it's very easy just to write down. It's just going to be a constant function in this notation. Just if it say y2 is positive, then it belongs here. Strictly. And again, boundness guarantees that there is exists unique solution. You can consider sometimes unbounded, but typically there are multiple solutions. However, there are typically unique solutions that grows sub-exponentially at most, that grows not quicker, not faster than a polynomial. This solution is typically unique. Now, it might be problematic to find in the literature a reference you really need, because sometimes people consider only such boundaries, but without allowing it being composed on a number of a finite set of subsets that satisfy this condition. So they exclude corners. Sometimes people directly exclude unbounded domains to make everything work. So sometimes it may be actually a big problem to find a direct reference for the result you precisely need. And probabilists often don't like to do that. They just use magical word. It's well known. And I am not even kidding. Like it's often the case. And everyone thinks that such a theorem should exist and should be provable, but never ever bothered to find a proper reference. Now, let we have function CB on the closure of this parabolic domain phi is bounded as the closure is just the boundary, whatever fxt is compatible on the boundary, and functions a, b, c bounded. Again, one can get rid of a lot of assumptions about boundness, and such that two important conditions hold. The first one is standard in the theory of parabolic equations. So the coefficient, the main part of our differential operator should be uniformly elliptic, or it depends on what uniformly elliptic means in a particular book. And exists some C, and for any I and G it makes sense, we have the following. Uniformly with respect to t variable, all these functions, including x, are Holder continuous with some alpha positive. Gx1t minus gx2t, the same for C, the same for B. They all should be less than some constant x1, x2, and also typically one also requires main coefficients to be Holder continuous with respect to time variables too. Then a standard result is there exists a unique solution. It has locally bounded derivative for every, say, dn from the previous proofs. It's going to have bounded derivatives for obvious reasons, but typically people don't require it to be bounded when you pass to the limit near a boundary. It's not really feasible sometimes. So there are a number of things to say here. So to end this lecture. So firstly, it's written in terms of A and not sigma. Recall that A is sigma sigma star. So it doesn't really talks much about the origin, the related SD. It doesn't require also coefficients to be Lipschitz continuous, which we typically wanted in the case of strong solutions. So it's slightly, it's not really compatible with strong solutions, it's more compatible with the whole theory of solutions, including weak ones too. There is an interesting moment that if we require Lipschitz continuity here, and this important condition holds, then the square root sigma is called a square root in a proper sense of A, is actually also Lipschitz continuous, which is not entirely intuitively clear why it should be so, because if it's x and take a square root, it loses Lipschitz continuity. But this condition guarantees that it is preserved. If this condition is violated, this is not true. The square root of the matrix, of a Lipschitz continuous matrix, may not be Lipschitz continuous. And this is something that in the end corresponds to uniqueness. Because to construct a solution for this But typically one uses the parametrics method and some potential theory, classical potential theory, to prove the existence. But to prove the uniqueness, typically one uses some form of maximum principle. And this is very related to that stuff. We are not going to discuss this in detail. So next time we will continue quick discussion of such results, but very quick, and we will switch to something in a probabilistic world. And exists. And that's all for today. Does anyone have questions or comments?
Just one organizational thing. You can turn off the record, I think.
Good.
The recording.